On to some content with special thanks to Greg Jacobs, John Frensley, anybody else who's helped me along the way so I can help you. First of all, scalar means direction doesn't matter. Things like distance, kinetic energy, time, speed, pressure, work. Direction doesn't matter. Remember that you can have a negative work quantity, but that does not mean it's a vector. Vector means direction does matter. So your velocity, displacement, momentum, acceleration, forces. For vector addition, we're going to use tip to tail, which means if we need to find A plus B, we're going to take the tip of A and move it to the tail of B, and then draw our hypotenuse. And that hypotenuse will be our resultant vector. For vector subtraction, we're going to do the same thing, but we're going to use the anti-parallel version of B. Vector notation, specifically for physics C, we will sometimes run across unit vectors for any of our vector quantities. Could be forces, could be displacement. We have 3 coordinates, x, y, z, and those coordinates are designated with I hat, j hat, k hat. Both of those are alphabetical, so you can remember which is which. The I hat represents x, j hat represents y, k hat for z. When you have these unit vectors, you're going to add, subtract, multiply, or divide components and leave the answer in the I hat, j hat, k hat form. No need to worry about combining. Remember that magnitude means absolute value. There is no formula for magnitude. It just means absolute value. Slope is the slope or derivative of position versus time is velocity. Slope or derivative of velocity versus time is acceleration. The area or integral of an A versus t graph is velocity. And the area of a v versus t graph is displacement. We have 3 kinematics equations, which can be used as long as we have constant velocity. First of all, the no displacement equation, the no time equation, and the displacement equation. If you memorize those, that's great. It's going to save you a second or 2 seconds doing 2 clicks to get to your reference sheet and then get to the appropriate section. If you don't memorize them, they're there, but at least memorize those names and what they kind of look like. These equations can also be used in the y direction. If we have something in free fall, then we'll have acceleration in the y direction as little g, which we're going to just use as 10 meters per second. The definition of free fall is when the only force acting on the object is gravity. So the only time your acceleration in the y direction is going to be when gravity is the only force acting. V equals x over t is not a thing. It's not an equation that you're going to use, because that real equation is the average velocity is our displacement over time, or time interval. For projectiles, we're going to remember to treat x and y completely independent of one another. Time, however, is the thing that's going to join your x and y directions. A bullet fired will hit the ground at the same time as a bullet dropped. We have initial velocity in the x direction equals v naught times cosine theta, and v naught in the y direction is v naught sine theta. If there's no mention of drag or air resistance, we're going to assume that it's too small to matter. This means our acceleration in the x direction equals 0, so we're going to get a term to cancel out for that displacement formula. We have 2 types of projectiles that we're going to mainly worry about. First one is an object that's launched at an angle. For that, draw the trajectory. That trajectory is going to be parabolic, which means we have symmetry. So whatever happens on the way up is going to happen on the way down, but opposite direction. That also means if you calculate the time at the top, where v naught y equals 0, that is only half the time, so we still have to double it for the total time. For the horizontally launched projectile, we're going to use x equals v naught xt plus 1/2 at squared, but there is no a because no air resistance. This is known as range. This can be for something that is actually launched. It can be a ball rolling off of a table. It can be a cart falling off of a table. It can be a rubber band launched horizontally. It can be water being ejected out of the bottom of a jug. All of these things, anything that has that second half of the parabola. This is what we're talking about with horizontally launched projectiles. And then to find time, we're going to look to the y direction. Presumably we have a known height, and we can rearrange the equation to solve for t, and then plug that t into the x equals v naught x times t. Our vertical displacement versus horizontal displacement graph is going to resemble the trajectory of the object. Terminal velocity happens when a equals 0. So that means when all of your forces balance out. If we're deriving for velocity before terminal velocity, physics C, it will be a differential equation. For example, mg minus bv equals m times dv dt. For any differential equation that we come into, remember, differential equation implies that we have a changing quantity. Could be a changing x, could be a changing acceleration, whatever it is. We have some changing quantity, so we use the math of change. To figure this out, we're going to use separation of variables, u sub if that's your thing, or if it's appropriate. Then we'll integrate with the correct bounds. We're going to integrate the left side, and we're going to integrate the right side. And then we're going to end up with a term like equals negative bt over m in there somewhere. Just really depends on the situation, because you can start with any function.